Hi. Let's do an applied optimization problem together. We're going to design a cylindrical can of volume 900 cubic centimeters, which uses the least amount of metal. There's some assumptions here that like the thickness of the metal is uniform across the can. But for me, these problems all start with a picture. So let's draw a cylinder. Excuse me. Okay, so here's my cylindrical can, and the volume equals 900. I'm just going to write down what I know. I'm just going to make up a symbol. They didn't tell me to use V, but I did it. I used the volume, was 900. Okay, so step one is draw a picture. Boom. Step two is label everything. We're going to label absolutely everything we possibly can within reason. Okay, so there's like a center point in the center of this. There's the radius. We should probably call it R. Why would I call it anything else? This cylinder has a height, and I might as well call it H because I like H for height. Okay. So it uses the least amount of metal. We're going to try to use the least amount of metal. Okay, so the amount of metal that's used is equivalent to the amount of surface area. So we use the least amount of metal means that we're going to minimize the surface area. Because the more surface area, the more metal. The volume of the thing is constrained to be 900. So we can make it be like tall and skinny, or like short and squat, or we could make it be like well proportioned like this. Usually it's some sort of like well proportioned thing, whatever that means. So when we say design a can, I think we mean find the radius and height. Okay, so we want to find R and H that make that happen. We're going to minimize the surface area. Minimize the surface area. Minimize, optimize. Surface area, ooh, I think that means that the surface area is my objective function, which I'm going to call omega. So even though, so I'm going to initially write it down as surface area, and then I'm going to relabel it as omega. Okay. So we need the surface area of a can. We need the surface area of a can. Let's see here. There's the top and the bottom. And then there's the size. And then there's the total. Okay. So surface area, top, bottom, sides. And then the total. The top is the area of a circle. That one's pi r squared. The bottom is also the area of a circle, pi r squared. And the surface area of an open cylinder is as if I had a sheet. So if I cut along a seam and I unroll it, then the side of it looks like, I'm going to erase this pretty quick here. So I've got a thing. This is, it's H tall, right? It's H tall, and this is the side of the can. And this distance here is if I unrolled that. And so this right here is the circumference of a circle, which is 2 pi r. So I've got essentially a rectangle of 2 pi r by h. And so the side, really there's only one side, okay? The side is the product of these two things, 2 pi r h. And so the sum of these things, I've got the top, the bottom, and the side. I've got 2 pi r squared plus 2 pi times r times h. And this is what I'm going to minimize this right here is the surface area. This is my function, omega. There's a problem. Omega has multiple variables. Omega depends on r and h. I got to get rid of an r or an h somehow. I got to substitute it away. Okay. So let me transcribe omega equals 2 pi r squared, top and bottom, plus 2 pi times r times h. So we got to get rid of one of these, and I think the right thing to do is to get rid of the h because there's only one of it. If I try to get rid of the r, it's in two places, and one of them is squared. Oh, no. So I'm going to eliminate this. I'm going to substitute away this h, and that's going to come from my volume. So in a lot of these problems, you end up with a multivariable objective function. What looks like multivariable, and then this constraint right here, which we haven't used. And if you haven't used your constraint, then probably a little off base. So this constraint right here is going to be the thing that lets me substitute that away. So let's do a little bit of side work, and then we probably can erase it. So the volume is 900, but we can also express it in terms of r and h. Yeah, the cross-sectional area of this cylinder, so the volume is equal to pi r squared, that's a circle, times h, which is the height of the thing, and the sum of this 2 and this 1 right here is 3, and volume is a three-dimensional measure, and so like dimensionally speaking, that seems to add up. So let me erase a little bit of the annotation that probably is not going to be particularly helpful. So pi r squared h is a useful thing to remember in terms of volume. Don't need that. Don't need that. Oh, and check it out. I happen to know that the volume has to be 900. So I know that I have to have 900 right here. Okay. My objective function is this. It's multivariate. It's got an h in it, which I want to substitute away. I'm going to obtain the h from through this right here. So knowing that 900 is equal to pi r squared h means that h is equal to, let's divide by that, h is equal to 900 over pi r squared. So this right here is going to get substituted in. So I have my objective function, omega equals 2 pi r squared plus 2 pi times r times 900 over pi r squared. So let's do a little bit of simplification. Let's let some r cancel. So I'm going to cancel an r and an r. And I'm going to, you know what? I'm just going to do it by, I'm going to cancel like that, cancel like that. We'll cancel a pi. The 2 and the 900 are going to combine. So this is equal to 2 pi r squared plus 1800 over r. So it's like a parabola modified by like this 1 over r function that's been scaled quite heavily. It'd be useful to like take a look at a plot of that if you wanted. Okay, so that was a little bit of work we did to arrive at a new objective function, and then we're going to want to optimize that function. In order to have enough room to do that, I think I would like to rewrite this up here. So I still have 2 pi r squared, and then this part right here changed on the back. Okay. Okay, so right there I should have 1800 divided by r. Okay. So this was all side work. So I'm going to erase it. Of course, on my piece of paper, this is like somewhere off to the side and I'm not going to erase it. These problems take up a whole piece of paper. If you try to cram it into like one line, like, don't do that because it's not going to work for you. Just use a whole paper. Be willing to do drafts of your problems. You know, like start over if things aren't going well. If you're getting frustrated, walk away. Ask for help. It's going to be okay. Our objective is this function. I want to find the minimum of that function. The minimum is going to be located at a critical point or on an interval. So my interval, or at an endpoint of an interval. So my interval of interest is from r is in 0 to infinity. If I have r is 0, then it's infinitely thin and infinitely tall. And if r is infinity, then it's squat and infinitely wide. So I think it's pretty clear that the optima aren't going to happen at the boundaries, just by that qualitative argument. So that's to say omega goes to infinity at both 0 and infinity. So my objective function must be like a little dippy dip. Okay. So we need the critical points. We need the critical points. The critical points are where omega prime equals 0. Okay? So we need omega prime. Let's take the derivative with respect to r. I'm going to get 4 pi r minus 1800 over r squared. Yep. And I want to know where that's equal to 0. So let's add 1800 over r squared to both sides. And I'll have 1800 over r squared is equal to 4 pi r. Let's multiply both sides by r squared. So that's going to cancel on that left-hand side. I'd love to show all my lines, but I'm totally going to run out of space. So now I've got a cube right there. And we're so close. Let's divide by 4. And so I'm going to get 1800 divided by 4 is 900 divided by 2 is 450. And then let's divide by pi. So that's equal to r cubed, which means that r is equal to the cube root, that's a straight line, I'll fix it in a second, of 450 over pi. A little happy with my marker. There we go. We are so close. Again, what's our objective? To minimize this function, to design a cylindrical can, which means coming up with r and h. Okay, I need to find the radius and the height. We found the radius. Now we need to find the height. Okay. Okay. Let's see here. So, I think we're going to need the volume relationship again because we know the radius, but I don't know the height, and the thing that couples those two things together is this 900. Recall that 900 was equal to pi r squared times h, which means that h is equal to 900 over pi r squared. Okay, h is equal to 900 over pi r squared, 900 over pi times the cube root of, now I'm not going to write that squared. I'm going to write it to the, 2/3 power. 450 over pi to the 2/3. And that's a number, which I could mash into my calculator if I really wanted, and which I could make effort to simplify if I really wanted. Probably I should like deal with these pi's, and I'm not going to, because I would probably just mash this into my calculator. So I've got these two expressions right here that give exactly the dimensions of my can, and we found the dimension first in terms of the radius by getting a univariate objective function in terms of the radius. We had to do a little substitution away in order to get it. We could also, like, if we plotted this function, which we totally could, we could observe that the minimum occurs at whatever value this is if I were to do it in terms of floating point numbers, which I did not bring a calculator, so I can't do that. Okay, so that was the process. It was like draw a picture, label everything, come up with the objective function, recognize constraints, objective function, optimize, find a value, find the other value, and finally, we should conclude that the dimensions are r equals and h equals, and put those numbers right here to conclude. I'm not going to replicate those numbers. I think circling them was sufficient. Hopefully you found that instructive. There's kind of like a really wide variety of problems for this applied optimization, and we just keep coming up with like new scenarios. So get good at them by practicing these. Just like go to the book and find the ones that you can do and do them, and then go find ones that you find challenging and try to do those. It's important to practice both things that we're comfortable with as well as things that we are uncomfortable with in order to really gain mastery. So I just want to say thank you so much for your kind attention today, and good luck with your applied optimization. Bye.